Yeah, you have to take it. All right. Thanks everybody for coming. We are very fortunate to have Pierre with us today. Pierre is based in ESSEC now, as a full professor there at the stats team. And a lot of bit about the infrastructure. So you're basically in the same team with Pierre Jacob and all these people in France that you probably all have heard about. But you're in Singapore, so he gets the best of both worlds. Before that, Pierre was based in Tokyo, and before that, he was based in Paris. So he's seen quite a lot, and he's done a lot of interesting research on the intersection of statistical learning theory and Bayesian methods. So he's like a really interesting outlook on both fields, and he's going to talk to us today about a bound that I remember because it defines a measure over measures. So I'm really looking forward to it. Thanks for coming, Pierre.
Okay. Thanks a lot for the invitation for being here. Yeah, that's a work that so it's actually the continuation of something we started with Dimitri a few years ago when I was in Japan, and Dimitri was supposed to join the team in Tokyo, but could not because there was at that time something you might have heard about the pandemic. And so it's something related to meta learning, so I want to explain what it is. And I started also this one actually with a Japanese author, Charles Ryu, so French author based in Japan, and Abdelati, who was my PhD student a few years ago. So I'll try to explain actually what meta learning is and why it might be interesting to do it in a Bayes setting. First, I want to apologize. I like when people explain things clearly in talks, without too much formulas, with like visually clear applications. And with this topic, I could not find a way to bypass very heavy formulas. We tried to do our best in the paper to remove as much as possible, but it's just the thing that it's not that it's more difficult than anything else, but there are many objects. So there are many formulas, many indices. So I will try to spend some time motivating problem, saying that it's a real problem, even though it's notationally heavy. And then I will provide an overview of our results. It means that just give kind of, without assumption, very summarized version of the result. And then if you're unlucky and if you don't ask enough questions to slow me down, you will have the full view of the results, but you might want to skip it because I think that the main idea is there. And I just prepared this in case you want the full length version. So please, it's just because it's a little heavy notationally, I don't want to lose anyone. I really, there's not a lot of slides, so don't hesitate to ask questions during the talk, because I think that for this topic, it might be better than to wait until the end. Okay. I just want to apologize for one thing, and also to pay tribute to someone who sadly died recently. Sometimes I make jokes, and I know that, okay, when it's joke about my own talk, it's fine, but when you make jokes about Bayesian or about fragmentists, it might be more painful. So if there are jokes about Bayes in this talk, like there is one in the first, I thought that there was one talk. But like, if there are jokes about Bayes, it's not meant as a criticism, but actually in this slide, in this set of slides, I tried more to do something as a way to visually remember actually what we are doing. So sorry about the jokes. That's the one. Okay, so many non-Bayesian statisticians would see Bayes as a kind of methodology where everything is like you just follow a recipe. Okay, so you have your big pot, you put a prior, a likelihood, and a sample. And I've introduced notation that I will use in the whole talk. The prior will be pi, parameter will be theta, the likelihood P of x will be theta, sample x1 to xn. As I will have many samples in this talk, and I summarize the sample as S. Okay. You put all that in the Bayes pot, and then you get your posterior pi of theta given x1 to xn. That's actually proportional to the prior times the likelihood. Okay. I just want to mention, this is why actually I have this introductory slide, that in this talk, I'm going to focus more on kind of generalized Bayes versions of the kind of things you're interested in, Jeremiah, and probably many other people here, where actually we will consider not necessarily a likelihood, but more generally a loss function, the kind of loss function that you have in machine learning. Okay, so 0-1 loss for classification, quadratic loss for regression, etc. So that would be like the modern computer science oriented version. You still have a prior, you still have a sample, But you have here a loss function of x theta. And think typically of the case where x is a pair object and label, and n and theta corresponds to whatever you want, either linear regression or a neural network or any model. And actually, this is the classification error. Okay, it might also be a likelihood, but I will consider a more general case where this one is included as a special case, but it doesn't have to be a likelihood. And in this case, there's been a lot of interest, I think, in machine learning, the machine learning community, in kind of pseudo posteriors, where defined like here as rho, which is actually inspired by this, obviously. It is the prior times pseudo likelihood, which is exponential times minus parameter alpha times the sum of the losses. Okay. Obviously, if the parameter alpha is equal to 1, the exponential of the sum is the product of the exponentials. And if this is a log likelihood, you will recover a minus log likelihood. You will recover this exactly. For some reason, when you are dealing with losses that are not necessarily likelihoods, there are theoretical results saying that it might not be the best idea to take alpha equal to 1. So I have to, in this like modern version base, I have to take into account this also, and I will have this additional regression. Prior, loss, sample, and alpha. And then actually, of course, the way to choose it in practice is something else. We'll discuss it later, but we have to take it into account. It seems that in some models it matters. Okay, so that's the so I will make assumptions, and I just want to say that, as I said, something will be heavy. So as a balance on the another side, I wanted to keep things simple. So I will work with IID data and the bounded loss. And many of the results, most of them can be extended to non-IID data, to unbounded losses that require a little more technical assumptions and a little more terms in some of the bounds. So in order to clarify the main thing I want to discuss today, I will keep these assumptions during the talk. Okay. So essentially, machine learning theory, we focus about the generalization risk, which is actually the expectation where a point X will be drawn from the same distribution as the data, but it's an unknown point. And I want to say, okay, on future data points that I have not seen yet, I will be able to have a small loss, which means that I have a parameter that will predict well. Okay, so that's what is measured by the generalization risk R. And our objective is to find, if possible, a parameter that will minimize this. And different with statistics. In statistics, you will have to find a way to make this parameter unique, etc., identifiability. But here we will not care about interpreting the parameters. So if you just focus on making R small, it doesn't matter if this R mean is unique or not, actually, but you want to find something that minimizes. Now, if I consider my base procedure, remember from this, okay, I take the right part of the, so it's generalized base, pseudo base, very well. The risk of this procedure, it's been like, okay, the expectation of the empirical risk of this prediction risk when theta is integrated according to rho. Then obviously, a good pseudo-based procedure should make this small. So I will state, it's not our result, but I will state a result that was known before, but that's a motivation for this work. The result says that if you use the base procedure I introduced before, so prior times e to the minus alpha times the sum of the losses, then actually what you will have is that in expectation of a sample, then the risk of the base procedure is as good as the risk of the best parameter unknown. Okay, so I'm not comparing to the best frequentist procedure, I'm comparing to the best possible risk, even the frequentist doesn't know, when we have to use instead of rho an estimator theta hat. Okay. Plus some rate of convergence, which sometimes can be improved, but in general, the best rate of convergence you can have is a constant, like it's not, I assume that the risk is bounded by 1, so this constant here is not something complicated, it's just 4 or 8, I don't know, and actually it would even appear maybe in the proof later, times square root of a dimension times log over n. What is D here? Because I did not introduce D so far. Actually, I could have written more generally a complexity measure of the parameter space theta. It appears that in many models it matches actually the intuitive notion of dimension. But in general, I will give the definition of this. It's actually a measure of complexity of the problem that will depend on two things: the prior of the parameter space and the distribution P, the actual distribution of the data. Okay. So I will just define D and comment on this later, but essentially, the meta-learning problem will be that we are trying to solve many problems. So we have many samples, and we want to learn many parameters at the same time. But we believe that they share something in common. So we could use the same prior pi on all of them. And the question is, in this bound, actually, in some sense, could we optimize in pi? So if you can learn pi from many different statistical tasks, maybe here you can have a pi that makes this D parameter smaller. Yes?
D does not depend on the choice of node?
Yes, actually it depends on everything. Usually people just write the dependence on pi and not on P or L. So I wrote P, but I forgot L. So that's totally correct. I will define it in the next slide. And I hope, so the definition is as follows. You have, so here that would be the parameter space, one-dimensional in this case. Here is the risk function, here the minimizer. And then you look at neighborhood of the risk function. Sorry, of theta star, but in terms of risk function. So what I mean, you look at the set of theta such that the risk of theta will not exceed the risk of theta star by more than S. And then you let S move, shrink to 0. And when you do this, so this region, I will call it N of theta star S. When you shrink S to 0, this region will contract to single bond here, theta star. And it's not only in my talk, it's something well known actually in Bayes theory, that what we measure the rate of convergence is how far this converges to the measure of this set converges to 0 under the prior. So essentially, and I think it's intuitive, right? If my prior has all its mass here, and I do not hope to recover theta star by days. Okay, so if it gives us the mass to this neighborhood that is too small, then things will not happen well. On the other hand, if I'm able to guess theta star beforehand, and I take my prior that is just theta star, Dirac mass, it's not realistic, but in this case, in this neighborhood, even if you shrink S, the mass remains constant to 1. So actually, the point is that the prior should not give a mass that is too small to this set. And the smaller it is, the worse we get your rate of convergence. Okay. Now, how comes that it is? So first, maybe I think the last line on this slide, exactly. So if the prior of this set essentially is lower bounded when S is small, it doesn't have to be aware, but when S is small enough, it's lower bounded by some S to the D, then actually D is the rate that you have in the convergence here. Okay. So of course, I did not prove it. I'm asking you to believe it. I will give some hints on how it's true, but this is what happens. Why is it a good measure? Why is it related to the dimension? I think that here, you see that this region is more like a segment. And when you shrink it, actually, you can expect indeed something that might be proportional to S. If you are doing the same thing and the parameter space as dimension 2, this will become like a kind of big parabola, 2D parabola. But then this region will become a circle. So when you shrink it to 0, the scale would be in S squared. And in dimension D, you expect S to the D. If it's actually, of course, it's a little more complex. It depends on the shape of the landscape, of the risk function, etc. But essentially, you expect something that will be locally like a dimension. Does it make sense? So how to prove the theorem? And I just want to explain it only because actually some tools that we will use in the sketching proof will be reused later for the meta-learning problem. It appears that one of the ways to rewrite the pseudo-posterior is the minimization of a penalized problem. So it is the minimization of problem with respect to P probability distribution in theta. Or actually, you minimize on the one hand the empirical risk, which is like if you want to minimize the real risk, capital R, which is like expectation. You don't have the expectation, but you have an empirical mean to approximate it. So you minimize the expectation of this when theta is 1 from P. And if you only had this term, actually, it will boil down to finding a P that would be a point mass at the empirical risk minimization, which quite a common approach in machine learning. But in the base version, you penalize by the relative entropy or the Kullback-Leibler divergence between P and the prior. So if you do this and you just renormalize this way, you obtain exactly this as so 0. So it's a way to see it. Now the point is, of course, we're not trying to minimize, the empirical risk here. We're trying to minimize the real risk. And you can use statistical probabilistic or deviation inequalities to say that one is not too far from the other. Actually, there are these two. So I will not cover the proof of this, but I hope it's a little intuitive that it's possible to prove that if you minimize the empirical version of the penalized problem, it's like minimizing the real version with the real risk here. You have a little loss. And the way I renormalized everything was just that the penalization becomes exactly equal to this alpha here. It's kind of coincidence, okay? So you would like to minimize this. You don't know. If you minimize this instead, something terrible might happen. But if you minimize the wall here, then you minimize also the true risk plus a little reminder actually here. Okay. Still okay with the notations and everything? It's fine. Okay. So essentially, this inequality that says that if you do this, you have this is like you have various versions of it in either fact-based literature or mutual information bound literature, but it is what it works. And then actually, the point is, if you want to recover the rate of convergence I gave here, one way to do it is to say that as this one reaches the infimum of the bound here that you have here, you can choose the P you want here. And what we do to make computations explicit, it appears that the trick is to choose P that will be not pi, but pi restricted to this neighborhood. And you consider all the versions where you would try to minimize the bound by taking the prior, but taking only its restriction to a neighborhood of the real, of the best parameter theta star. So if you do so, essentially, depending on assumptions you have, so I told you it's like this kind of sketch of the, okay, you don't need additional assumption. Yeah, no, sorry. So if you take the neighborhood, so the set of point theta, such that the risk of theta is smaller than the risk of theta star plus s, then obviously under this posterior, expectation will be smaller than risk of theta star plus s. And now it's just like 2 lines exercises. Derive a formula for the Kullback between pi and pi restricted to some set. And you find that it's log of 1 over pi of this set, actually, which turns out to be, by assumption, remember that we assume that pi is larger than s to the d. If you take the log, you have a log of 1 over pi is smaller than d log s. So this is exactly what we have here. Then you optimize in s. So you write this as a function of s here. You optimize it in s, and you have an explicit choice for s, which gives you the bound that we had before in square root of d log n over n. Yes.
Question here. The bound in the frame, the left-hand side integrates over the distribution of the samples.
Yes.
But the right-hand side, the sample should be somewhere on the right-hand side, no?
It's not, because actually it's integrated. So you see here, it is, for example.
Yeah.
But the point is that if you use fact-based bound in expectation or you will obtain this actually, where actually the sample disappears, because here it's integrated on the sample, so it does not depend on the sample anymore.
Okay.
And I really say,
okay,
you have this. So
yeah.
If you write
This is
your
not a high probability bound, right? It's not an expectation.
exactly, if you write the high probability bound, you would have not that here probability, and then you have both versions. You know, you have the version with the empirical, but you can also prove a version with the true risk here. But yeah, okay, I chose to write everything in expectation. Okay. So that's how you prove this. Now, just a little digression about that, because it will be actually a surprising result that will come later. But
Pierre, just one question about the last point you made, that you basically switch between the empirical and the true risk. Is that because you've assumed the loss is bounded and then you can just apply Bernstein? Yeah.
there is here a happening inequality applied somewhere. Bernstein is already too complicated.
Okay.
Yes. Essentially, if the loss is not bounded, you will have assumptions to get this kind of results. But
and then with Bernstein, you could do with sub-Gaussian losses, presumably, or something.
with happening, you can do with sub-Gaussian too, actually.
Okay.
So if it's sub-Gaussian and the variance is bounded by 1, we would have the same actually. So yes, even with happening, actually, you can do sub-Gaussian. But I just want to put also now. Yeah. So there's one remarkable thing which will actually useful later. So I said rate is square root of d log n over n. Sometimes it's the best you can do. It's proven there are lower bounds, but it's not always the case. So there is a very old result actually, even like in the Vapnik bounds in the 70s, etc. They said, okay, you minimize the empirical risk, you will have square root of Vapnik dimension, which is related to this d actually over n. But if you have a perfect classifier, you don't need the square root. Okay. Here it appears, and I will not prove it, but it appears that you have the same thing. So if the risk of theta star is 0, then you don't need the square root here. And that's a very old result. But little by little, various communities started to make various assumptions that will lead to the same thing. So actually there is, for example, the more general Mamel and Sivakov margin assumption is cited quite often in the literature. The special case is no noise, like above. But even with some noise, you still have a version of the Mamel and Sivakov assumption with some noise, but the noise is controlled and it still leads to d log n over n. And completely different point of view, more based on optimization. Bartlett and Mendelssohn, they have a paper where they prove that if your loss is both Lipschitz and strongly convex, then actually you have that too. Does not depend anymore on the noise level, but more on the shape of the loss. So completely different assumptions lead to faster rates. And a little later, people realized that there was a general way to write it. So there is a Bernstein condition, which was named Bernstein condition because actually when you have Bernstein condition, you can make a better use of Bernstein inequality. So it's nothing that Bernstein was aware of probably, but still you can make a better use of Bernstein inequality and improve the rate above. It's completely abstract. You say that the expectation of L of x theta minus L of x theta squared, star squared, can be controlled by the difference of the risk. So in some sense, you can remove square magically. And I don't really have an intuitive, maybe you have, but I don't really have an intuitive interpretation of this quantity, but it appears that actually people were able to prove that this condition, this condition, this condition all imply this one, and this one implies the fast rate. So it seems that this one is the central one actually. So it's not another condition, it's really something that is the way actually you prove the fast rate without the square root. All the previous condition imply this one, which seems to be more general. And one final remark is that if you want to do things practical, if you want to use your stochastic gradient algorithm rather than MCMC on very large scale problem or whatever, then actually instead of minimizing over all probability distributions, you can minimize on a subset like Gaussian distributions or mixture of Gaussian or whatever. You can define a variation posterior like that, and then optimize the parameters of this Gaussian using stochastic gradient. And actually, there were a few papers, but we have, for example, one with James Duet and Nicolas Chaudin, where we proved that essentially, not all the time, but under very minimal assumption, either on the loss or on the prior, etc., it works in the same way. So I summarize the result. The risk of your Bayes procedure in expectation is as good as the best one, plus a constant times this dimension times log over n to a power beta. But actually, I'm not complicating things, it's just that I wanted to write 2 in 1, right? So beta is 1 if you have the Bernstein assumption, no noise or margin or whatever, and it's 1/2 otherwise. To be honest, there is intermediate situation, beta between 1/2 and 1, but the set of known examples is less big. So I don't know, but yeah, you can have a wide range, but essentially we will focus on slow rate and fast rates. Yeah. Okay, so far nothing about meta learning. It's a lot of information about Bayes. You have this generalized Bayes procedure. You have this result that tells you that your Bayesian risk is as good as the best possible risk plus d log n over n to the beta. Beta is 1/2 of 1. And to all that, to summarize, like I want to summarize all this into 2 remarks that I could have done without introducing all the theorems, but then it might have been a little less clear. I don't know. The generalization error is driven by actually a rate of convergence that depends directly on d, which depends on time. So as you would expect, do we need the theory to say that or not? You know, like, as you would expect, if you choose the prior well, things might be better than if you choose it not well. But here we have a measure. I'm not even saying that it is what will decide whether a prior is good in practice. As we have something quantitative, we have something that will tell you that some priors might lead to worse rates here, and some priors will lead to maybe good rates. So one possible way to measure what is a good prior. Then the question, can we learn pi? You're doing pack-based bounds, think, okay, I will try to minimize the right-hand side. I might want to minimize it, but this is not an empirical bound. It's not a data-dependent bound. And actually, in the pack-based bound, the prior is fixed. You learn the posterior from the prior and the data. You're not allowed to learn the prior. All that is still part of the introduction, but now I come to the meta-learning problem. So you assume that you have many data sets, but all from the same fields, all from the same application, but maybe, for example, different countries, different group of individuals, etc. So you have maybe the same set of variables, but say, for example, each of them is a different distribution. Okay. So the same data sets, same loss, and you're trying to solve all these problems. And traditionally, we would each solve our problem separately and publish a paper about it. The point is, if we believe that actually all these problems have something in common, the parameters might be close to each other. The parameters might be quite, they don't have to be exactly the same, but similar tasks might have quite similar parameters, etc. We might want to at least choose the same prior in all these problems. And then what we will see is that in this case, by using the other task, it might become possible to optimize your prior for one single task, actually. And of course, if the tasks are absolutely unrelated, it will not help. But if they are related, it will help. And I will provide a few examples. So we might want, because the tasks share some similarities, we might want to use the same priors. On the other hand, in this case, can we optimize it and can we choose it so that it's to a better bound? So I want to say, I think it's a problem that is nice in practice. I've seen cases. So there was a guy called Makoto Yamada in the American IIP who was working actually on such meta-learning problems. So the idea is that he had observation on patients and assumption that these observations were from a linear model, but the linear model is not the same for each patient. Each one has a parameter, and this parameter will decide whether this treatment works or not, etc. Point is that for each patient, you don't have a lot of data. So individually, it might be difficult to estimate the parameter. Now, if you think that on the whole population, the parameters are distributed, for example, like a mixture of Gaussian that would correspond to 2 subpopulations, you might want to use this mixture as a prior. And you think that it might help maybe to estimate with a little number of observations, to estimate faster for each patient in the model. So it's really motivated by applications. And I really think that this might be a nice problem in practice. On the other hand, the results I will show today are mostly theoretical. They will say that there exists a method that can reach this rate, learning the prior. I'm not sure that the method we propose is the one that should be used in practice. So there's still a gap to fill, but at least it says something.
There's a question here.
Yes.
You say again, I think I missed it. What is different between the different pictures?
Here?
Yeah.
They are
What would be different between the different?
So if you think in terms of likelihood, for example, each of them would be same model, exponential with parameter lambda. but each of them might have a different parameter and a different sample. So you can use maximum likelihood estimation in all of them. But if I give you the additional observation, the additional information that all the parameters are quite close, you might want to use Bayes and learn a prior that would be actually very concentrated around the, you see what I mean? So each of them, different optimal parameter, theta star, different sample, and I will recap the notation in the next slide actually. But still same problem structure, same parameter space, I can use the same prior. Okay. Yes.
Sorry, just to make sure I understand it correctly, this is basically hierarchical Bayes or generalized Bayes.
This is, yes, in some sense. Even though, as usual in machine learning, we will not focus on learning correctly these parameters. That will focus more on learning a prior that will allow for a new, not yet observed sample to learn as fast as possible the new parameter. So it's more a predictive, yes.
Keep with the questions. So you say many related tasks, and I guess you gave some examples. Is there like a way to formalize this? In this literature, how people formalize what are related tasks?
Indeed. So for example, if you look at, maybe Dimitri, you remember that, like the papers by Massini, Miano Pontil, and its co-author. In some of them, for example, they have the parameters of each of these tasks are themselves IID from another distribution. So in this case, it becomes fully hierarchical. Okay. On the other hand, the way I choose to write things is more like this kind of this kind of inequality in that infimum actually somewhere, where actually in the inequality you will see something that depends on all the tasks, and you will see that it will be small if the tasks are related. And the way to be related would be to make this small in some sense. So it gives something that is larger. For example, we will have results where the rates can really cancel before the tasks are the same. And then the constants become super small if all the parameters are quite close. But I don't want to assume directly that the parameter of each task are IID, because I think it's more global than that. Even if they are not independent, but they are still close, it will still work. So, but yeah, definitely in the literature of data learning, there are many approaches. Yeah. Sometimes people assume that the tasks are related in the sense that they are IID from a distribution on the task space, and that they are in a really smaller subspace actually. So I told you many samples, each of them from a different distribution. It might be that the optimal parameter is not the same, so I will recap the notations. Sorry, this is where it gets heavier than our cheesecake. But so we have T tasks. So T will be the number of samples, the number of tasks. Okay, each one of them, the xi are IID from the distribution P1, P2, etc. Oh, actually, we do in this case. Sorry, I did not remember actually, but yeah, in this case we do actually. We assume that the J's are IID from some distribution. So we have the distribution over distribution. Sorry, so that's we have that in this case, yes. And then in the task T, I cannot write the sample S anymore because it depends on T. So it's ST and it will be XT1 to XTN. It's IID from PT.
Sorry, so it's the same P for all the tasks?
No, because you see here, the task T corresponds to sample XT1 to XTN. It's IID from some PT here, and all the PT they are IID from some. So you could think, for example, all of them are exponential with parameter lambda, but then the lambda itself is IID from a distribution on lambda. So that's yeah.
And the results only say something about how things change with the early P, like does it need to be more concentrated?
Yes.
Okay.
Yes, exactly. We have one that depends on the variance of P or this kind of things. So it's exactly the objective. Yes, that's what happens miraculously. So I just need, actually, it's just reminding you all the notations, but adding a T index because everything depends on T. So you have the generalization risk in task T. Now, okay, the best error in task T, but the theta T star depends on the task. So for example, here, you will see that you will have some results where the rate will depend on the variance of theta T star, actually. If the theta T, and it's interesting because it means that even if the tasks are not exactly the same, but they have the same parameter, obviously it's easier to learn this parameter. So you don't have to assume that they are exactly the same. But overall, one of the things would be, are the theta t star similar? And other cases covered in the literature would be, are the theta t star, even though they're not all the same, they belong to the same subspace, for example. Have the pseudo posterior that depends on the prior, on alpha, and on the task t. So I keep all the dependencies explicit now. And then the objective now. So in some sense, these tasks are for training. So I don't really care about doing the best I can on all these tasks. But what I want is more like a kind of predictive way. I want to be prepared to face the next task. I work in the business school, so I think that in this sentence, I want to be prepared to face the next task. Is selling point of it. I want something that will say, okay, I have all these tasks, but if a new one comes from the same distribution, I don't want to know the parameter in advance because each one has its own distribution. But from the previous task, I want to learn a prior that will make me ready to learn the new parameter as fast as possible. Yeah.
It's too many questions to tell me, but so the loss function here doesn't depend on t. Is that just for simplicity, or is it?
You could, in the sense that it's true that you could have the same variables and sometimes have logistic regression and sometimes linear regression. Still want to learn some common subspace because the variables would be the same or whatever. To be honest, we wrote it with a fixed loss function. And in some version, I promise the extension works perfectly. The various L, it might be, but we have to think about it a bit. So I cannot promise. Probably you can say things, but probably have to think about a little about what is really possible and what is not. So I cannot promise, but it makes sense.
But any loss would have to be defined in the same parameter space, right?
Yes. But it can be same parameter, but for example,
Yeah,
logistic and linear regression. So now, let's imagine a new task, PET plus 1, comes from the same P here. And then a new sample comes. So xt plus 1, extra xt plus 1, n. So I want that if I use the same pseudo-based procedure, so rho, you remember the prior times exponential of minus the loss function, but with the prior pi at alert here, then I obtain prediction risk that would be smaller than someone who would come, and obviously this is a very informal statement, I will come to the theorem in the next few slides, but that someone would come and choose to use a fixed prior that they decided. Okay, yes?
So, do we want this for all pi, or it's the pi you use to learn?
So, actually, yeah, it's kind of informal statement. So it's not, I would like, in practice, what I would like, if you choose a pi and you say, oh, it's my subjective prior as a Bayesian, then I would like to say, yeah, by learning from the previous task, I do something better. Actually, we'll see that we have indeed an infimum over all pi plus a learning rate, as usual. So it's just a two-stage based procedure. But so sorry, this statement maybe is a little anyway. So just to summarize things, because I want to summarize notations to a point. So that's the distribution on distribution. There's a name actually, it's called the environment, I think, in the Massey's paper, right? Then you have each of the distribution, which gives a sample here. And then that's the new task. We don't know it yet, we don't observe it, and then we will have a corresponding sample. So in what comes, I will sometimes take expectations on the one hand on all this, which should be considered as usually in statistics, the expectation over the sample. So it's the expectation over what I have in hand. And then for my prediction error, I will take expectation with respect to this. So I should write integral with respect to S1, S2, etc., P1, P2, etc. It's not very convenient. So instead, I introduce colors. The past is red, and the expectation will be written as expectation with respect to the data in red. The future is blue, okay? And I will write expectation with respect to the new data. So just convention. Okay, with the notations. Okay, so then let's switch to the overview of the results. And I want to explain what you would have if you knew the truth, what you would have if you use always the same prior, and how we can improve on it. So we always compare to the oracle, like usually to the R theta star. The theta star is the best, we don't know it, but if we knew it, this is the best performance we could get, okay? Here, imagine the perfect oracle. Someone, you give this person a task and the person immediately knows what is the best parameter. This person will just reach the risk over a new task, theta star plus 1. In expectation over all the tasks, I will define it as E star. So that's my ultimate objective. No one can do better than that. If you believe in randomness, there's the best you can do is to predict the best theta star, but you cannot do better. So this is the uncompressible error. Now, take someone who is a subjective Bayesian and who would not be aware of the previous samples or do not want to use them, but instead want to use the subjective prior pi that reflects Bayesian. So I will write this as E of pi, and it's the expectation of the risk if you use the pseudo base posterior, or because if it's a likelihood, it's actually the base posterior, okay, with a prior pi. And actually, from the previous chapter, if you just take the risk bound in one model and you integrate it over the distribution of the data, you will find that this would be E star plus the same constant as before, okay, times the expectation of the rate of convergence. So always the log n over n to the beta, but you have this d, and the d depends on pi and pt plus 1. So this is why actually I did not highlight L, but mostly pi and p. We see that it depends on p. Because it depends on p, I have to keep the expectation here, and it depends on pi. So essentially the same rate as before, but in expectation. And now, actually, what we are going to do is to learn a prior, which hopefully will improve on this rate of convergence. For example, by getting a minimum here. So, yeah, I still have time to remember. In order to, because the result is a little convoluted in the paper, in order to clarify things, we will start with a simple setting where we have a kind of Bayesian tournament. So you imagine Christian Robert, Nicolas Chopin, they all come actually to a Bayesian tournament, and each of them brings his or her own prior. Okay? And they say, no, my prior is the correct one. It reflects my subjectivity, but as often in research, we all think that our subjectivity is the best one. So they believe, okay, my prior is the best one. And I'm just saying, okay, based on the past data, I will learn which one is the best, and I will be able to do as well as the best. So now, finally, I can define our procedure in this special case of just fixed number of priors. Remember that rho T of pi alpha, I told you, the pseudo posterior, is the minimizer over a set of probability distributions. For now, no rational base. It's the set of all probability distributions of the expectation of the empirical risk plus the KL between P and pi over alpha n. And for short, I will write this as RT of P and pi. Okay. So I say pi is fixed. In one task, I minimize this in rho to get my pseudo posterior. Now, if you have T task, I tell you it's fine, you can minimize in pi. Okay. So if you have T tasks, just take the mean of these quantities and minimize in pi. Okay. So I just observe on all the tasks which of my Bayesian friends gets the best performance, and then for the future, I just choose to keep the best performance. Okay. It appears that in this case, we have two things. It might seem obvious, but then you will see that there's a kind of miracle somewhere. So the expectation on future data of the error of the pi we learned on past data is actually the minimum of the errors that you get by using each of you get the best of your Bayesian friends, plus a learning rate which is in log k over t. Okay. So from now, I would say it's nothing like a miracle. As usual, you learn between a final set of things. You can do as best as the best one, as good as the best one, but you have a price to pay for learning. Now look at the rates here. Remember that this error here, I say, is the E star. Fortunately, like if n and t are large enough, we converge to the best E star. It makes sense. But the E star here was d log n over n to the beta. Remember that beta is 0 or 1, 1/2 or 1, depending on whether or not you have this Bernstein assumption, mysterious assumption. The expectation here is from, okay. But with respect to the subjective Bayesian approach, what we gain here is that we have a minimum. So if one of them is much better than the other, you gain something. Okay, you improve the rate. At least if one of the priors was not the good one, you can detect it and discard it. But look at, for me, where the miracle is here. Here, to learn the parameter using Bayes, you have d over n to the power 1 or to the power 1/2, depending on whether Bernstein assumption is satisfied or not. Here, you always have to the power 1. You never have the slow rate 1/2, which was for me the point where I said, okay, now maybe there's something curious happening here. Actually, it's not just 2 layers of learning over learning, and then, okay, we have a procedure that is not practical, but it leads to, but it seems that there's, for me, something surprising is that to learn the prior, okay, people usually use the Bernstein assumption to quantify the difficulty of the task. No Bernstein assumption, difficult task, very noisy. Bernstein assumption, easier task, less noise, or it's easier to detect the signal. But it means that when you try to use many tasks, you use Bayes in many tasks, and then you want to use the many tasks to find the best prior for these tasks. Then, in terms of learning, it's always an easy problem. It's not on the difficult side. Yes?
3 minutes.
3 minutes. Okay. Well, I mean, that's essentially the main result. The point is 2 remarks, though, actually. Even if beta is 1, you have 1 over n and 1 over t here. So if you decrease a little d here, but here t is equal to 2, it's not worth it. So our results mean that we can prove that our procedure of meta-learning is interesting if the sample size is small in each task, but you have many tasks, which makes sense. If you have a task with infinitely many points, we know from asymptotics that you don't really care about the prior, you know the true parameter. But if you have a very small number of points in a sample, then maybe the choice of the prior becomes more critical. So it would make sense. On the other hand, let's not overinterpret this. We don't know if the bound here is tight or not. It might be improvable, but for now, this is work only if you have many patients, but small number of sample per patients in the example I mentioned before. But yeah, the most striking thing does not depend on like the rate of convergence inside the task does not influence the rate of convergence across task, which is quite surprising. What we did then, maybe I can summarize in 1 minute, but then we tried to do a procedure where we don't have a finite number of priors, but we try to learn a prior over infinite set, say all Gaussian priors. And essentially, we still recover that you do the best of them plus some complexity over t, so you never have the square root, even in the infinite case. It's kind of the miracle still goes on. And for example, Gaussian priors, interestingly, the rate would become this. So p is the dimension of the parameter. So without meta-learning, you have p over n. With meta-learning, you have p over t plus p over n times log of 1 plus nv, where v is the variance of the parameters across tasks. So which means that if v is 0, or if it's close to 0, then just using like caricature things, if v is smaller than 1 over t, then actually just using log of 1 plus x is smaller than x here, the n vanishes. You just have something that depends on t. So if all, which makes sense, if all the tasks are have a parameter that is super close, it's better to learn the same parameter for all the tasks and not to rely on the 1 over n that might be small, if that might be large, sorry, if the sample size is small. But, and is it okay that I still show 1 slide maybe?
Yeah.
We have other examples that are less trivial, like mixtures of Gaussian, for example. But then if you assume that maybe, because you assume that all the tasks are the same, in the end it's easy and it's a little, but I told you might have many and we did not have time to explore all the possible configurations. All the tasks are not the same, but the parameters live in a smaller dimensional variety and you might want to learn that variety to be your prior. It might become even more notational and even worse, but simple case, actually all the tasks are not the same, but there are clusters of tasks. So actually there are, for example, 5 parameters and each individual might be different, but in the end, the parameter is in one of these 5 clusters. And then in the end, in general, the rate would be this one. But if the variance within each cluster So you have a P over N, dimension over N. But if the variance in each cluster is small enough, this term vanishes. So you still have a term in 1 over N, but it's no longer the dimension of the parameter, but only the log of the number of clusters, which might be much smaller. In huge dimension, but with 2 clusters, you transform something that depends on the dimension of the parameters to something that only depends on the number of clusters, right? Because asymptotically, your prior will be a mixture of 2 Dirac masses. So it does not matter what the dimension of the space is. In practice, it will be just a 2-point space. Okay? So that was the overview of the results, and as promised, thanks to your questions, we did not reach the view of the results, which is fine. So thanks a lot.
Then we have some questions. I'll let you do it.
Okay. Before you went to the method, you said you introduced the parameter T that quantified the coverage of the prior of the area around the theta star. Yes, this. In the same way, you have multiple tasks and for multiple theta stars. Does this become a stricter condition because you now need the same prior to cover these multiple regions, multiple theta stars? Does this
Yes,
become
the condition should be satisfied in each model actually. So it's true. In some sense, usually we write this condition on theta star, but of course, if you, this is the theory says that it should only be true around theta star. Now in practice, if you think in terms of being an applied Bayesian, you cannot build a prior that is concentrated around theta star because you don't know theta star actually. So the point is, for example, in RD, you will take a Gaussian prior, or you will take if you know that the parameter is in the bounded region, you will take a uniform prior. And these choices will lead to rate D that will be uniform on a set of parameters, or maybe might depend, actually, it might also depend on theta star. So I would not take this as a way to build priors around theta star. Actually, these conditions, sometimes you should probably think of something like these conditions should be satisfied around not only one parameter theta star, but around a large class of parameters, so that I can reach the rate of convergence for all these parameters. And typically, for example, if your, it's easy case, but if your parameter set is a ball in RD, then using a uniform prior on RD will reach this actually, for example, usually. So yes, sorry, I wrote it, which is the minimal requirement over theta star, but in practice you don't know theta star, so you try to make it happen. And the best way, if you don't want to favor some parameters with respect to others, the best way to do it is to spread the mass. But the larger the dimension, the more costly it is, which again leads to this dimension thing.
If there's a question in the chat as well, maybe I'll get up and
So in more kind of, let's say, frequentist method learning, one thing that's done a lot in theoretical results is to also somehow take into account the optimization algorithm, something like this.
Yes.
Is this where kind of you expected more formal result was? Because I guess you talked about variational at some point.
Oh no, actually, so variational, unfortunately, that's something. So first variational, and then I will answer about the specific optimization algorithm. We have here something weird that happens. Is that this result where you have on the one hand maybe 1 over n or 1 over square root of n, but on the other hand 1 over t, is something we can only prove for base, not for variational base. For some reason, it's purely technical. It's really like some, algebraic form of the solution in the case of exact base that we don't have for variational inference, and in fact, we don't know how to prove it anymore. It might be true, but we don't know how to prove it anymore, which for me is an important question. So this is one of the open questions in the end of the extending this to variational approximation. So to be more exact, the exact procedure relies on priors within each model and then one prior over priors on the whole model. So we can do variational on the higher okay, but not inside the task, which is very frustrating because we know how to define Bayes for variation model usually, but not for meta learning. And I say that I know the result you mentioned, like for example, I know this paper by Machine and OpenC, but there are other authors working on meta learning. They would say, for example, I will use gradients, stochastic gradients in each model to learn the theta parameter. And then in the end, I do as well as the best stochastic gradient algorithm, best in terms of with the one with the best gradient step, for example. The one with the best initialization.
I think this is somewhere you would have an extra term which would decrease with the same number of iterations.
Yeah, I know, but what I mean is that one thing that's different, and I don't know any result like that, is that see here, like this E star is not related to any algorithm. It is the best parameter in each task and integrated over all the tasks. And from what I know, but maybe I don't know all the papers on this topic, especially like we wrote that almost 1 year ago, so there might have been new papers since. But all the papers I know, they have here the error over the best version of your algorithm. So you use stochastic gradient, you have the best initialization, the best step. But then they don't write explicitly how this connects to the best error and integrating with it, which sometimes can be technically a little annoying, and with Bayes it works fine. I agree that they will have then actually, of course, things that decay with the number of iterations, the number of, but not sure that you converge to the best.
Yeah.
At least I haven't seen these kind of things written. So you would have two results: being Bayes and compare yourself to the best Bayesian. But here we are saying we are doing Bayes and we compare our posterior to the best ever, statistic Bayesian or non-Bayesian, the best performance reachable by any algorithm, actually. So that's something I wanted to write properly.
Is there some interpretation or some intuition as to why the alpha no longer features in the bound once we switch to the variational approximation?
Yes, because I got a lot of, how do you say that in French, it's just under the carpet, it will not make sense in English, but it's still there, sorry. Like if you have, in this proof here,
yeah.
So if you want to get the rate of convergence I mentioned, you have to choose S properly, but also alpha properly.
Right.
And the choice of alpha depends on whether the Bernstein assumption is satisfied or not.
Okay, so that Bernstein exponent is actually somehow containing the alpha.
Yes, so actually the point is that if Bernstein assumption is not there, you replace it by something that will go to 0, and then actually you don't need to tune alpha, you can take alpha as a constant essentially. So this proof is only in the case where Bernstein is not satisfied.
So that's alpha goes to 0 in the limit of n or in the limit of tasks?
Yes, in the limit of n. So actually here you would have, okay, this is the proof without Bernstein assumption. So you have an alpha here, and in the end you have to take alpha in something like 1 over square root of n. In case where you use Bernstein assumption, you have alpha times Vn, and Vn tends to 0 when n tends to infinity. Okay. So then actually you don't have to take alpha as 1 over square root of n, you can take alpha as a constant, which means that theoretically alpha, I did not mention, actually not that I did not mention how to choose alpha in practice, but I mean, it's a difficult problem, right, to learn this temperature parameter in generalized Bayes. In theory, you know that if Bernstein is not satisfied, it should be 1 over square root of n. If Bernstein is satisfied, it should be a constant. But which constant? In practice, it's not easy to calibrate. So it's there. Whether you do variational or not, and whether you're doing meta learning or not, the problem remains there, actually.
Okay, well, thank you.
So it's a difficulty, but yeah, I just didn't want to emphasize it too much because the talk was more on the meta learning side, but this difficulty does not disappear, actually. So there are, in my PhD thesis, actually, there are some procedures, for example, where actually you use this for many various alphas, and then you use the procedure to choose alpha. It makes the thing completely impossible, but in theory, you can learn alpha. But it's really not practical. It's just to prove that it's possible, but I'm not aware currently of the procedure to choose alpha that would be at the same time good in theory and good in practice. I'm just aware of some that are good in theory and some that are okay in practice. So that's it's an open, I mean, for me, it's the most exciting open problem in generalized Bayes now, but that's
I have one question. So when you present the last results on learning with Bayesian, is there a feasible scenario where let's assume you actually don't have tasks, all your data from a single task, but you're artificially chopping the data into tasks to then learn better prior? Do you ever benefit from that in this part?
No, I don't think so.
That's really short.
Like, when I talk to this result, not very foundation of that, but no, I mean, I don't think you can actually, and it's not,
I mean, you wouldn't do it in practice.
you will not do it in practice, but no, it's not, because if you start to chop, like, it's not, like, I did not say that we will move this term to replace by this one. You just decrease the constant in front. But if you chop your sample, you decrease n. So overall, the game will be destroyed by the.
I mean, you're kind of describing consolidation. You're kind of describing consolidation. Or you have hyperparameters where your hyperparameter is the entire line.
In some sense, like you would chop your, like cut your sample in many small samples, and say that to predict in one of them, you're using all the others to learn a prior or something. So there might be connections, but I don't think that this would lead to.
Yes, you're right. That's not a million mile work. That's an interesting image.
I'll ask a question. So you mentioned there's no square root there, but why is there no d there? It makes a dumb question. Is it it's the d term of the beta thing? There's no d term there, right? So
yes. So here it's because I did not. I just work on a very specific scenario where you just learn a finite set of priors. But then actually, sorry, remember I have to go fast. If you want to learn in an infinite set of priors, you have a term that I wrote C of Q, it's more like complexity of learning in Q, but which turns out to be like the D, actually, it's a dimension. So if you're learning Gaussians, then you will pay the price of learning the prior, the prior, so the mean and the variance of the Gaussian or whatever. So it's a dimension here in general.
Is anybody waiting?
Oops, so maybe we should. Yeah, okay. Yeah.
So I was wondering, I mean, as a subjective basis, if I had K primes, I would not choose one of them. I would have mixture on them. Like you did for the normals. What happens then in that result where you don't minimize over K, but you minimize over the weights of different?
So first, I don't want to say that this is absolutely not what you can do in practice.
Yeah.
But so then these are, and sorry to be like to hide myself and advance as a Bayesian, but beyond there is the big max theory actually there. Our results are, there is something uniform here. You don't see like if something, so it's actually a supremum over all possible scenarios. In the worst case scenarios, if one of the prior is very good and all the others are terrible, it might be artificial, but in this case, the mixture will be quite far from that.
Yeah, okay.
So with the mixture, you will not do as well, actually. Now, on the other hand, if we were to compare your strategy and mine in practice, I quite believe that I would need a huge number of tasks before this strategy becomes better than a uniform mixture. But definitely, if you imagine that you have many,
sorry, it doesn't have to be right. You have to learn. If I had enough tasks, I could learn.
Okay. So you're suggesting to take a mixture of the priors, but to learn the weights of the mixture.
Exactly.
Yeah. So actually, okay. Then in this case, I agree, and this is actually what we do here in some sense.
Okay.
So I say that you can okay, you have the two, but our procedure here. So I took the mixture here, the minimizer here, but actually it works as well. If you learn optimal, this is more the pack-based spirit actually. You learn here a pi, that will be a mixture here, and you learn the weights. So you will have to minimize this in terms of the weights, but you will have another KL penalty. And the results say essentially that you would have the same upper bound. But in practice, it would be better. Yes. In this case, it would be better. So I just wanted to write the simpler version with the minimization. But actually, in the rest of the paper, the other results, everything is given in terms not of learning one prior, but it's done in terms of learning a mixture of all the priors that ultimately concentrates over the best prior. So actually, this is what we do. Yeah, okay.
All right, I think we need to Okay, Alquier, unfortunately. Goodbye. You're joining us upstairs, I hope, for tea and some biscuits, so if you have any questions.
Okay.
Oh, yes, the Yule log. Yeah, let me get you.
Just what, I'm gonna fight for it.